Okay, a very good morning to you all from a somewhat overcast but dry Galway. I hope you're keeping well wherever you are joining us from today. This is the 22nd in our series of Signpost webinars where we examine the science, policy and advice underpinning farm sustainability in Ireland. My name is Mark Gibson and I'm manager of the Teagasc Connected programme. If you'd like to receive updates on training opportunities, latest publications and invitations to Teagasc events, I encourage you to sign up today to the Teagasc Connected programme for free. You can do that by visiting www.teagasc.ie/connected. The Signpost webinar series is being brought to you in association with Dairy Sustainability Ireland, the National Rural Network and Food Drink Ireland SkillNet. You can send us your questions by clicking on the Q&A tab at the bottom of your screen. And today's session is being recorded and will be available afterwards to view on the Teagasc website and YouTube channel. So today we're going to look at the role of renewable energy and how we can improve the efficiency of energy usage on farm. And to discuss this, I'm delighted to be joined by two Teagasc experts in the area. Dr. John Upton is a research officer based in Teagasc Moore Park, and Barry Caslin is an energy specialist working with the Teagasc Farm Management Programme. You'll be asked, John and Barry, you're very welcome to this morning's webinar. Barry, can you hear us okay?
Yeah, good morning, everyone.
Good morning, thanks, Mark.
Great, John. And how's all down in Cork today, John?
Can't complain. We're getting a brief respite from the recent bad weather, so all's good.
Right. And Barry, what you're up in Roscommon today?
Yeah, Roscommon, yeah. It's a bit overcast, but it's not raining at the moment.
And sorry, Pat, we didn't introduce you. Pat, you're down in the sunny southeast of Wexford, or what's it like there today?
Southeast today.
The grey southeast, great. Well, Pat is your program manager for the Teagasc Environment Knowledge Transfer Programme. So it's good to have you there. You're going to be helping us out with questions at the end. So Barry, we're going to start with you today. You're going to give us a presentation on renewable energy and gives, I suppose, an idea of the macro picture. You've been working in this area for some time now, Barry, is that right?
Yeah, I've been in the Teagasc Advisory Service since 1998, and I joined the specialist program back in 2006, which was in the area of energy. And I suppose I took on the area of rural development in the last number of years as well. But yeah, I suppose renewable energy really took a great hold of interest there back around 06, 07. There was a lot of interest from farmers, and maybe especially on the biofuel side of things. And in more recent years, then it's other technologies like energy efficiency technologies and other renewable technologies like solar in more recent years. And of course, energy crops have been to the fore there for a number of years also. But I suppose it's only now that we're seeing a lot of traction in this area, especially it really links into this whole area of decarbonisation, reducing emissions within the agricultural sector. But I suppose a big point about energy emissions and agriculture as well is the fact that it's saving emissions, not just within the agricultural sector, but also within the energy sector. When you're using the likes of biofuels and bioenergy crops, that is helping other sectors to decarbonise as well.
Great. And John, you're a researcher in this, the area of energy efficiency. You've been involved in some interesting projects over the last number of years.
Yeah, I guess I started as a researcher back in late 2008, and my first project that I worked on was actually dairy energy efficiency. And I suppose like we've done kind of the hard miles in terms of auditing farms, modelling energy flows, and quantifying the effect of technology on energy flows through dairy farms. And I think we're really at an important point in time right now when it comes to this topic, because we have the technologies, we know that they work, and we're just waiting for the levels of adoption that we need to get the results that are required in the long term. So I think it's really, it's the right topic for this time at the moment. Since then, of course, as well, I've worked on other topics like water consumption on dairy farms and milking efficiency and milking technology. But, I still have a great interest in the energy side of things. And coincidentally, it's the area where we have the most research done as well. So.
Great. Okay, John, we'll be coming back to you after Barry's presentation. So Barry, if I could ask you to share your screen, and we'll hand over to you for your presentation. And do remember to send us your questions during or after the presentations using the Q&A tab at the bottom of your screen. So Barry, yeah, that's coming up nicely, Barry. So we'll hand over to you now.
Thanks very much. Good morning, everybody. So just to give you an idea about, okay. So just to give you an idea about, I suppose, a reminder of the key agricultural emissions that we have out there. And I suppose the main ones are carbon dioxide, methane, and nitrous oxide. And that's just a breakdown of those different emissions within the agricultural sector. And as you can see, the largest one by far is methane, which is produced by natural byproduct of enteric fermentation from cattle and bovine animals. And you can see there 64% of our emissions are coming from there. Carbon dioxide, which would be a consequence of the burning of fossil fuels. Also the application of lime is about 5% of our emissions coming from there, are 0.94 megatons of CO2 equivalent. And then nitrous oxide, which comes from the spreading of fertilizers, like nitrogen fertilizer, the 6.3 megatons of CO2 equivalent coming from there, which is about 31% of the agricultural emissions. So the energy side is very, very little in comparison to the enteric fermentation and also to the nitrogen fertilizer application. So it's only a very small proportion. One thing I'll be referring to in this presentation is the whole area of emission factors. And I suppose this slide is quite important because a lot of people like to understand what is my emissions when even in my own dwelling house. So there's emission factors that are associated with different types of energy generation. So if you take grid electricity, the emission factor for that, and these are on the SEAI website, Sustainable Energy Authority of Ireland website. You can see the grid electricity emission factor at the moment is 0.375 kilograms of CO2 per kilowatt hour used. So if you look at there, take an example of that, a typical dwelling house would use 4,000 kilowatt hours of electricity per year. So that's, if you multiply that, those 4,000 kilowatt hours or units of electricity by 0.375, that's emission factor is 1,500 kilograms or 1.5 tons of CO2. And you can do a similar formula there for kerosene oil. If you're burning 1,000 liters or 2,000 liters, you can see the tons of CO2 that you're using in your house every year. Most of those emission factors stay the same every year. Like natural gas, coal, kerosene, those emission factors stay the same. What has changed quite a bit over the last number of years is grid electricity. And that's, like, I remember back in 2010, grid electricity had an emission factor of over 0.6. Now it's down to 0.375, and that's mainly due to the likes of wind and more renewables coming on stream and feeding into the national grid. If we look at possible on-farm generation, the main types of on-farm generation that we could be looking at is micro hydroelectricity schemes, solar panels, ground source heat pumps or wood fuel burners, wind turbines, growing trees for forestry, short rotation forestry or energy crops, such as willow or miscanthus, which could be used as a biomass fuel for sale or for their own home supply. So there's various options there. And another opportunity for on-farm energy generation is the installation of an anaerobic digester or biogas plant to produce biogas, which could be used for electricity or heat production, and which also could be upgraded. That raw biogas could be upgraded to biomethane and injected into the gas grid. Invest in renewable energy, it does offer an opportunity to generate an income through government incentives, and there are some government incentives there at the moment, which I'll be talking about in a while. And we've seen right across Europe, renewable energy is an opportunity for diversification and to generate an additional income to the core farming enterprise. It makes use of on-farm resources like slurry, forestry, straw, wind, river resources to generate energy. Energy generated can be used to generate additional income and also reduce greenhouse gas emissions, not just in the agricultural sector, but in the energy sector as well. In terms of energy awareness, I think this is the most important area that we start off with our first fuel being energy awareness, reducing the amount of emissions or energy use that we're using on our farms. And then after that, we introduce the renewable technologies. So I think it's important for businesses as a farm is to develop tools to create awareness among staff. You know, there's a lot of businesses where many staff are working there, and it could be literature, signage about turning off lights, and SEI offer a range of training and supports around energy management. I'd recommend people to look at the Energy Training Academy and there's very good information there on reducing emissions within various sectors. There's also opportunities for classroom-based energy management training for companies, and that can be organised by the likes of the Sustainable Energy Authority of Ireland. There's more, I think, more effective use of thermostats, time clocks, motion sensors, and insulation within the likes of pig units, poultry units. It would be very, very important. Vehicle checks and maintenance. I think that a lot of people underestimate the importance of that in terms of fuel efficiency. Also maintenance of boilers. Existing boilers that are there at the moment, you know, your efficiency could drop, even on an oil boiler, could drop from 90% maybe down to 60% without servicing. Assess, I think, on-farm storage facilities, for example, potato stores, to ensure that insulation and natural ventilation is utilised and energy is used efficiently in those buildings. I just wanted to give examples because I could go around on the various different enterprises like pigs and poultry and horticulture as well, but I just want to give an example of, you know, where lighting and where various types of technologies can reduce emissions within the sector. And if you just take a pig unit, lighting accounts for one of the greatest inefficiencies on pig units. Fluorescent lighting can lower energy and can reduce costs by up to 80%. There's still a lot of tungsten bulbs still being used on pig units. And LED allows you to match the lighting levels and the color the animals need. So LED is an even better technology, which 5 or 6 years ago I would have said is still not at that point where it's commercially applicable, but it's very much so now, and it makes a lot of sense and will give payback. So fluorescent stripping lighting can also reduce. If you look at a lot of pig units at the moment, they're using the tungsten bulbs, and some of the most inefficient units could be anywhere between 2 to 4 kilowatt hours per pig produced in terms of lighting energy use. But if you change that to fluorescent strip lighting, that can reduce that to 0.8 kilowatt hours per pig produced. So if you take that kind of a saving of 3.2 kilowatt hours per pig produced, that could be a saving of 1.2 kilograms of CO2 per pig produced. And that's based on that emission factor of 0.375, which I had on my very first slide, which is the emission factor for electricity generation in Ireland. And that's just another example of LED lighting, and where you just change from a 116 watt bulb fluorescent tube to a 25 watt LED light. Exactly this light, lumens of light. And if it's been run for 14 hours per day, I won't go down to the whole example there, but based on that example, you get a saving of 174 kilograms of CO2 just for changing that bulb. Selecting high efficient pumps, aerators and separators, and again this is relevant to the pig sector. It should be considered when specifying or upgrading motors for feed or manure handling on pig units. Fitting a variable speed pump can reduce cost by 30%. Inefficient motors typically require 6 kilowatt hours per pig produced. Most efficient motors, which are the variable speed pumps, will be down to 2 kilowatt hours per pig produced, because the pumps come on when the demand is actually there. You're getting a saving there of 4 kilowatt hours per pig produced. So you can see straight away there's a saving there of 1.5 kilograms of CO2 just for moving to the high efficient pumps, aerators and separators in that example. Then if you look on a pig unit, insulation, a good insulation reduces the amount of heat lost and the heat coming in as well at certain times of the year where you're trying to control humidity levels. So heat loss to the walls of the building requires supplementary heat and increases the cost. Fitting composite panels containing solid polyurethane insulation protected from moisture ingress is recommended. So the typical insulation that would be on pig units at the moment would be quite poor, and you're talking about 9 kilowatt hours per pig produced of energy required. Whereas if in a best practice situation, you could reduce that with the insulation applied down to 3 kilowatt hours per pig produced. So that'd be a saving of 6 kilowatt hours, which works out at 2.25 kilograms of CO2 per pig produced just by improving the insulation. Also in ventilation is designed to optimize the living conditions of the pigs. So typically a finishing building ventilation fans use 7.2 kilowatt hours per pig produced. In a best practice scenario, you could achieve 4 kilowatt hours per pig produced, so saving of 3.2 kilowatt hours. So that works out at 1.2 kilograms of CO2 per pig produced of a reduction in CO2 in the pig units by improving the ventilation system. By fitting efficient fans, a single fan in a finishing building will consume its own value in 12 months. So the point would be that by paying 10% more for a more energy efficient fan will pay for itself in the same amount of time. It's very, very important as well to look at things like cleaning dust and debris from fan blades. A typical finishing building would use about 10 kilowatt hours per pig produced for the fans. But the best practice scenario would be 6 kilowatt hours per pig produced. And that could be a simple thing like cleaning and dusting the debris from the fan blades to make sure that the fans are running as efficiently as possible, giving you a saving of 4 kilowatt hours per pig produced, which works out at 1.5 kilograms of CO2 per pig produced. So they're kind of a suite of measures that could be used on a farm, on a pig unit. It's applicable as well to poultry units as well, where those kind of savings can be made. Just wanted to draw your attention to a scheme that was a pilot scheme that was run for 3 years, 2017, 2018 and 2019, funded through the Sustainable Energy Authority of Ireland, which gave a 40% grant towards variable speed drives. And they paid out 228 grants during that time. You get an electricity reduction of about 56 to 65% by using variable speed drives. So you can see there that scheme, which grant aided for 288 farms, led to a CO2 emission reduction of 288 tons of CO2. That's assuming a 50% reduction in the electricity being used during the milking process. So I think it was a very, very worthwhile scheme. It's not running for 2020, but I suppose there is an opportunity for something like that to happen again. And other technologies then, like that's kind of the efficiency side that I just covered. Then moving on to technologies that will be relevant to, a lot of agricultural sectors will be heat pumps. Many heat pumps will be in many domestic dwelling houses, air source heat pumps, ground source heat pumps, and they warm the water, they warm the underfloor heating system in a pig unit or poultry unit. They're mainly associated with underfloor heating. They can be used in certain cases for space heating as well. So LPG will be the main form, or propane gas will be the main form of heating, especially in poultry units at the moment. It requires increased ventilation. It requires higher CO2 and humidity levels when you are using those types of fuels, and that's why air source heat pumps negate that requirement for increased ventilation. So underfloor heating systems, air exchange units, and backup LPG heaters is what would be required in that kind of a situation. Many pig units have air source heat pumps already installed around the country at the moment, and they're working very, very well. They use a compressor and they work on what's called a coefficient of performance. It's around 1 unit of electricity would be used to run the compressor, would generate around 4 kilowatt hours of heat. So they are quite efficient. I also want to talk about the role of biogas in production in greenhouse gas mitigation. Biomass production. So carbon is sequestered through the process of photosynthesis. So the plant is using carbon dioxide. It's using water and heat, and it's taking carbon dioxide from the air to produce plant tissue, and sequestering carbon from the atmosphere in the soil and in the biomass. It also mitigates against nitrous oxide via reduced nitrogen requirement, because biomass crops have a very low nitrogen requirement, and because there's a lot of indirect energy used in nitrogen production, you're negating and mitigating against nitrous oxide usage within agriculture as a result. So you're reducing emissions associated with fuel usage and the manufacture, excuse me, and the manufacture of inputs, fertilizer inputs, and your substitution fossil fuels for energy generation and heat production. Just draw your attention to the MAC curve, which is the marginal abatement cost curve. Any of you who's signing in for this series over the last number of weeks would be familiar with the MAC curve. This is just the energy side of it. So we're talking about the use of biomass, wood chips and perennials, that if you're below that line there, you can see that line going across there of 0. If you're below that, you're cost neutral. If you're above it, there's a cost associated with the reduction of carbon reduction or carbon mitigation within energy production in this particular element of the MAC curve. So you can see here that the low-hanging fruit is the likes of farm energy savings on the farm. What I've just been talking about, there's a quick win and there's a saving. It's not a high cost associated with it. And assuming all these, there is a high cost when we start going on to technologies likes of anaerobic digestion and biogas. There is a higher associated cost per ton of CO2 abated. You can see there the cost is coming in at almost €300 per ton of CO2 in the case of biomethane. So some of these have a high cost, some have a lower cost, but if all the measures that are recommended or that are outlined within the MAC energy sector were achieved, that would be a reduction of 1.37 megatons of CO2 equivalent in agriculture. So they're the type of savings that could be achieved. There are different assumptions in that. There's assumptions on the amount of energy crops that will be used. There's assumptions on the amount of forestry. Forestry will be one of the biggest players in that. I just want to draw your attention as well to supports that are there for renewable heating. And it was introduced in 2019, the SSRH, or the Support Scheme for Renewable Heat, and tariffs were introduced to support renewable heating. And I think this is very relevant again to pig units, poultry units, the horticulture sector especially. And you can see there's different tiers of tariffs. So the first 300 megawatt hours is paid at €56.60 per megawatt hour. And that works out at, if you're at tier 1, using 300 megawatt hours, which wouldn't be a lot, you'd be getting €16,980 per year. And it's for a 15-year period that these tariffs are paid. So the next tier you move on to is you get 700 megawatt hours, which is between 300 and 1,000, at €30.20 per megawatt hour, which works out at €20,650. So that's the way it works. So the more you use, the less you get paid. So there's no incentive to waste heat, because you see there in the table that it's actually done in cent per kilowatt hour, 5.66 cents per kilowatt hour at tier 1, 3.02 cents per kilowatt hour in tier 2. If you were buying in wood pellets, well, if you take oil, for example, or kerosene at the moment, oil would be costing around maybe 6.5 cent per kilowatt hour. Wood pellets, you'd probably be buying them in at maybe 4.5, 5 cents per kilowatt hour. So you certainly won't be buying them wood pellets at 5 cents per kilowatt hour if you're only getting an SSRH payment of 3.02 cents per kilowatt hour when you drop down to tier 2. So as you can see, the more you burn, the less you get paid. And I think it's quite a good scheme. There's quite a bit of interest in it there at the moment, especially in poultry units and pig units across the country. That's just an example there of somebody made an investment of 360,000 in a 400 kilowatt boiler. It was running for 1,700 megawatt hours per year. That's 50% load rate. It's not running all year round. You're displacing 160,500 litres of oil. You're making an assumption there on the cost of oil at 66 cents per litre. So there's two savings that can potentially be made here. One is a saving in the fact that you're buying in wood pellets or wood chip, whatever you're buying in, at a lower cost than the oil. And the saving here would be, in this example, would be €47,000 of a saving in buying in wood chip as opposed to buying in oil at 66 cents per litre. And no carbon taxes will be applied to the likes of oil, coal and gas, making those fossil fuels more expensive in the future as well. So that's the kind of saving that could be achieved there. But if we add the SSRH for 1,700 megawatt hours, which is this example here, that would bring an additional payment of €41,620. And we add those two figures together, the 47,930 and 41,620, the fuel savings and the SSRH payment for 15 years. You can see there that it's a saving of €89,550 a year, given a payback in 4 years. I think any renewable energy project, it needs a payback with under 5 years to justify farmers or anybody making that kind of investment. And this SSRH scheme is open to all sectors. I mean, there's hotels, hospitals, nursing homes, where biomass boilers are very, very relevant to. So you can see here they will get this kind of saving and payback. So the SSRH has been a welcome policy mechanism, creating demand-led policy.
Barry, we're just under a little bit of time pressure, so if you could maybe wrap things up a little.
Yeah, okay. Well, the greenhouse gas savings in that poultry unit are 437 tonnes, just in that example. So that's just an example of straw, that you can put a value on straw as well in terms of its energy value based on the weight and the kilowatt hours in it. Photovoltaics, again, another technology. If you take a 20 kilowatt solar PV array, you can be talking about there of 6 tonnes of CO2 that could be saved in that example. Biogas, again, it's a relevant technology as well. We have very little biogas in Ireland at the moment. There's probably 2 good agricultural plants there at the moment. There's a number of ones using sewage sludge, but I think we will see more developments in the whole biogas area, where the likes of grass silage is a fantastic resource that we have in this country that could be used to feed biogas plants and give farmers a land use alternative. I think we will see opportunities emerging there. There is a support under the SSRH that I showed the table for earlier for biomass burning and like wood chip or pellets. There's support here on the heat side of biogas production. Up to 1,400 megawatt hours will be supported. And you can see various tariffs. The first 2 tiers are the same. Tier 3, then you're down to a lower tariff, but it's a maximum payment of 31,500 for 15 years. So just to conclude then, and energy efficiency should be the first fuel on all our farms, not looking at putting renewable technologies into buildings that are inefficient or leaky or losing heat. There's a large variation in energy costs on Irish farms, and every farmer can calculate their own energy costs, and it is possible to look at their own energy costs and look at where savings could be made. This is probably something that could be looked at in future knowledge transfer groups or discussion groups where those kind of comparisons could be made. Payback periods on renewable technologies can vary considerably. Certain technologies will be relevant to certain farms, will not be relevant to others. And energy crops can mitigate emission productions within agriculture and energy. Thank you very much.
Thanks very much, Barry. You covered a lot in that presentation, so I suspect there'll be demand or interest from people to hear lots more maybe about some of those specific technologies spoken about there. What we might do is, John, we'll ask you to fire your presentation up for us, and we'll go directly to that, and we will then take questions afterwards. John, are you there? You can hear us okay there? I think you're on mute, John.
Yeah, I can hear you, Mark.
Yeah, that's great. Okay, I'll hand over to you, John.
Okay, can you see that okay?
You're in presentation mode there, John. Just you might need to just switch out of that.
Okay. Good morning, everybody, and thank you for joining. So I'm going to give you a brief overview of the energy efficiency picture and also some idea of what can be done with regards to renewable energy generation on dairy farms. So just looking at the topic, first of all, I guess from a macro picture, obviously there is an on-farm economic incentive to reduce energy use, but we'll say from a national emissions perspective, the work that we've done here in Moore Park for the last number of years shows quite clearly that we're using approximately 42 kilowatt hours of electricity for every tonne of milk produced in the country. It's projected that by 2020, Ireland is going to produce up to 8.8 billion litres, which will require in the region of 378 gigawatt hours of electricity. So that's roughly enough energy to keep Cork City going for 6 months. So it's a significant quantity, and that's just the on-farm portion. That's not the processing portion that comes afterwards. Therefore, our electricity-related CO2 emissions will be up in the order of 182,000 tonnes by 2020, unless we take some serious mitigation strategies and implement them. Just zooming back down into the farm level picture now, I want to give you an overview of where the energy is going and what's using it inside the farm gate. So we took a cross-section of 60 commercial dairy farms, monitored them in detail for 6 years, where we installed energy meters on every piece of equipment inside the farm gate. And across the board, we're seeing milk cooling is the largest energy user. On average, it represents 31% of the total on-farm electricity bill. That's followed on then by water heating in second place at 23%. The milking machine and associated milk pumps represent 20%. The other section there, the light blue section, that would equate to the winter sheds, the workshops and compressors, other miscellaneous items like that. That's coming to about 18%. The water pump is 5%, and lighting then is delineated last at 3%. So because of the detailed methodology that we applied, we're able to also tell when the electricity is consumed, which enables us to put a day rate and night rate onto the costs. And on average, across the farms measured, we came to a figure of €5 per tonne of milk or per 1,000 litres of milk sold, which is roughly equivalent to half a cent per litre in terms of production costs. And we're also seeing a massive variation across the farms, anywhere from €2.50 per 1,000 litres of milk, right up to €9 per 1,000 litres of milk. And you're right, that's a massive variation there. And it's never really down to one particular topic. It takes a concerted effort in those three main areas, really, of the cooling, the heating, and the milking, implementing efficiency measures in those areas in order to get from a relatively high specific energy costs down towards the lower cost there of the 250. Okay. If you're interested in how we deploy this methodology and some further details on the results, you can find them there in the Dairy Farm Infrastructure Workbook, which we published in summer of last year. Interestingly, there's also a simple energy audit worksheet in there and an energy usage survey, which enable you to both calculate specific energy costs on a particular farm just by filling in A, B, C, D through the sheet, and also do a brief energy audit of the technologies on the farm, which can help improve decision making with regards to projects on farm. The link is there on the bottom of the slide, so free to download, publicly available on the Teagasc website. Moving on now, we'll just briefly touch on the three main technology areas, starting off with the milk cooling. So we know that milk cooling is the largest energy user inside the farm gate, so it's conveniently also the one that you can make significant savings in relatively easily. I suppose there are two distinct cooling technologies that are deployed. First off is the direct expansion type system, which is probably by far the most common on Irish dairy farms. The direct expansion tanks are very efficient in terms of the amount of energy consumed per litre of milk, so we like them for that perspective. They have very high performance levels and they're quite cost efficient to buy. So as a result of that, they're really dominating the market right now. There are, I guess, some negatives to them in the sense that they do have quite a high requirement for peak energy demand. So the compressor sizes are relatively large. That's because the tanks themselves have to cool the milk as the milk is being produced. So you need fairly large compressor sizes on them, which may be an issue on farms where they're approaching their maximum import capacity in terms of what they can draw from the grid. The second type of bulk tank there that's available is an ice bank tank. These ice banks are ideally suited to build up a tank of ice at night time and harvest some of that night rate electricity, which is at a lower cost. And then that ice can be deployed during the day to cool the milk as it's being produced. So in terms of the positives and negatives of them, you can use them with a dual stage plate cooler, which is a benefit from a milk quality point of view. And in terms of the negatives, they do use more electricity per litre of milk cooled, and they are much more expensive to buy. The work that we've shown here in Moore Park would indicate that a person going out to buy a new tank in the morning would be better off to go for a direct expansion tank, as the return on investment for an ice bank in terms of energy savings alone just wouldn't be there. However, there are a couple of specific cases where the ice bank is a better option, mainly number one, on robotic milking farms, because the ice bank can provide a relatively gentle cooling for low volumes of milk that are being produced from the robot. And number two, where the maximum import capacity of the farm cannot be increased to accommodate a larger direct expansion tank. Okay. Now we want to move on to the energy efficiency option, and the technology of pre-cooling or plate cooling can be applied to either direct expansion or ice bank cooling systems. And this technology can reduce the energy use of a cooling system by 40%. So very, very effective. The mechanism of operation is that well water pumped from the farm well is used to take out heat from the milk before it goes into the milk tank itself. And the objective of that pre-cooling process is to cool the milk to within 5 degrees Celsius of the incoming water temperature. So for example, if the well water is at 10 degrees, our objective is to put the milk into the tank at 15 degrees. In other words, the plate cooler itself is taking out more than half of the energy from that milk. To achieve the objective, we need to have a milk to water flow ratio of 1:2. So for every litre of milk that flows through the plate cooler, we'll need to put through 2 litres of water. A variable speed drive milk pump is also of great benefit in achieving that objective because they slow the flow of milk through the plate cooler and give the water a good opportunity to cool that milk. Water pipe sizes are also critical. Any restriction in flow of water from the well through the plate cooler and out to drain slows down the water flow and decreases our milk to water flow ratio. Okay. Generally across the board, the pre-cooler or the plate cooler has the best return on investment of any energy efficiency technology that we're going to speak about today. Even without grant aid, the return or simple payback is usually less than 5 years. So this is a technology that's highly recommended, very trouble-free, no moving parts, and delivers the goods in terms of both return on investment and energy savings. So we move on to the next piece of equipment that we're going to look at, which is the milking machine, or more specifically the vacuum pump. So the vacuum pump within the milking machine will use 90% of the energy used at the time of milking in the milking machine itself. And the main option for improving the efficiency of this piece of equipment is a variable speed drive and the use of variable speed control. And the variable speed drive can reduce the energy consumption of the vacuum pump by over 60%. So very, very efficient and effective in terms of its objective. And the method of operation is really to replace the traditional vacuum regulator that is present in all standard milking machines with a vacuum sensor. That vacuum sensor in turn speaks to an inverter, and the inverter is responsible for changing the speed of the motors, therefore the speed of the vacuum pumps, in response to demand from vacuum down at the milking cluster end. So, for example, when no milking is carried out at the cluster end, the vacuum pumps will only be spinning at about 20% of their full capacity. And those inverters can take in single phase or 3-phase. So as Barry mentioned, there was a good grant by the SEI in previous years to support retrofitting of these variable speed systems onto existing milk plants. Unfortunately, that's not running this year in 2020. However, they are grant aided under TAMS for new milking installations. And I believe going forward, it'll be a requirement that all new milk plants going in will have to have a variable speed control. And as it happens, that is the most cost-efficient time to install a variable speed drive in the first place, is when the plant is being installed and commissioned when it's new. So we'll move on to the next piece of technology, and we'll speak a little bit about the topic of water heating. So water heating is quite an important topic right now, in the sense that a lot of farmers are moving over to chlorine-free detergents. And one of the key drivers of success with chlorine-free detergents would be an adequate supply of hot water at the correct temperature. So going forward, it's going to be vital that a farmer can hot wash both the milking plant and the bulk tank at the same time in the same day. And our guidelines for hot water requirement for the milking machine would be 10 litres of hot water per milking cluster at 80 degrees. And for the bulk tank, we're looking to heat about 2% of the volume of the tank, and that should be at 70 degrees, so it doesn't have to be as hot. As an example, if you have a farm with a 16-unit milking parlour, that would require 160 litres of hot water to wash that parlour. And if the farm also has an 8,000 litre bulk tank, that would be an additional 160 litres, which is 2% of 8,000, okay? Giving a total requirement of 320 litres of hot water there on that farm to hot wash both the milking parlour and the bulk tank on the same day. And what everyone wants to know is how much is that going to cost? So I presented here a table showing the cost of heating 100 litres of water with various technologies and their associated CO2 emissions per 100 litres. So if you look at day rate electricity, that's the most expensive. That'll be €2.10 per 100 litres of hot water. Moving on to night rate then, off-peak rate, that'll be 94 cents per 100 litres. And for both electrical systems, there's an emission factor there of 6 kilograms of CO2 per 100 litres of hot water. Moving on to gas or liquid petroleum gas, that's coming in about 87 cents per 100 litres with a 2.4 kilos of an emission factor. Oil or kerosene fired systems are the cheapest right now as oil prices is very, very low. That's coming in at 56 cents per 100 litres of hot water and 3 kilos of associated CO2 emissions. I suppose the important thing to remember with regards to the CO2 emissions are that they can be reduced significantly through implementation of either heat recovery systems, which we'll speak about in a moment, and also solar PV systems, which are ideally suited to link up with the electrical heating technology, as the dairy water heater is an ideal storage mechanism to soak up any excess solar generated. But we'll come to that topic in a moment. Generally, the guidelines that I issue are that the oil and gas-fired systems are worth considering from a financial point of view, where daily use exceeds 300 litres of hot water per day. And that's because the investment required to implement these oil and gas systems are higher than it would be for an equivalent sized electrical system. And that 300 litres is the point where the payback starts to make sense. So for the example we looked at previously, where we had the 16 unit parlour and the 8,000 litre bulk tank, that would equate roughly to our tipping point there, whereby the oil and gas fired systems would tend to pan out economically, okay? Just a brief note there on the night rate electricity. So,
thanks.
Again, it's vitally important to use the night rate to achieve economical heating on our electrical systems. The day rate is roughly 18 cents per kilowatt hour at the moment. The night rate is usually less than 8 cents right now. And the night rate hours are from 12 midnight to 9 a.m. So moving on then for options to increase the energy efficiency of these heating systems. The first one I'll mention will be the heat recovery unit. These heat recovery systems recover excess heat from the milk cooling process and store it in a tank of water, essentially preheating the water and reducing the power demand of the heating system by about 50%. So return on investments are quite good. There's a TAMS grant available. The ideal time to install them is when the bulk tank is being upgraded so that everything is installed and commissioned by the same installer and guaranteed as such. Secondly, we'll just touch on the topic of solar photovoltaic panels or PV panels. These are the panels that generate electricity from the sun. And I would see them being a vital tool in our arsenal really to tackle energy emissions, energy-related emissions from dairy farms. Currently, there's a TAMS grant available for them, up to a maximum of 11 kilowatt peak systems. Currently, the most popular size system going in is in the order of 6 kilowatt peak, which is ideally suited for our average herd size right now of 70 to 80 cows. The key thing really, I suppose, with regards to these solar PV systems is that right now they should be sized on the basis of a self-consumption only kind of a strategy, maybe with a little bit of excess leakage to the grid. But really where you get the value and the good returns on the investment right now is to size these such that 80, 85 or 90% of the power generated will be consumed within the farm gate. As an example of their efficacy in reducing CO2 emissions, a 6 kilowatt peak system installed on a 70 or 80 cow farm will reduce CO2 emissions by about 3 tons per year. The paybacks on them can be quite good. As I mentioned, they're eligible for TAM support at either the 40% or 60% level, depending on farmer eligibility. But they also do qualify for accelerated capital allowances, meaning that the purchase price can be written off against tax in the year of purchase. And in my view, the water heater, the electrical water heater, is an ideal storage mechanism to soak up any excess electricity for a particular size system, especially on the average dairy farm that would be installing your 6 kilowatt peak systems. Obviously, systems installed at a much larger level will need excess storage in the form of batteries and so on. But I think, in my view, as an effective means to generate a good payback, I would try to size them for self-consumption and use that water heater as the buffer storage for any excess electricity. So I appreciate that we've covered a lot of kind of the technical aspects of things. We've looked at numerous different technologies, and the payback of those technologies varies dramatically depending on what type of farm it's on, grant eligibility, and so on. So we've developed a tool to help guide decision making around this topic, and we've developed a decision support tool to help farmers make decisions around energy efficiency and renewable energy technologies. That tool is called the Energy Optimization Tool, and it's relatively simple to use. If we have time later on, I can give a quick demo on it. But basically, you log onto the tool, the address is there on the screen, or if you Google Dairy Energy Decision Support Tool, it's the first link that will pop up. And basically, we're putting in some simple farm details, which you'll see there on the left-hand side of the screen: farm size, milking time, milking parlour size, and so on. And on the right-hand side, we'll put in the type of technology that we want to evaluate. And this tool will give us our energy saved, our cost savings, and our simple return on a simple payback period. So very good, very important to evaluate just what type of return you would expect from a particular investment before you go ahead and make the plunge on it, okay? It also allows you to examine different levels of grant aid, which obviously has a massive effect on the simple payback period. So just to sum up from my talk this morning, I believe it is very, very achievable to reduce our energy use in dairy by 30% through the implementation of the simple technologies that we've spoken about today: the plate cooler, the variable speed drives, the solar PV, the heat recoveries, and also generate 30% of our power demand from renewable sources, mainly through PV. We have the knowledge and we have the technology on the shelf to meet our targets. The adoption side of things is our next hurdle, and I believe it's a significant hurdle. It's going to require policy and advisory and everyone working together to achieve the levels of adoption that we require to meet those targets. And luckily, we have a decision support tool there. It's available online. It's free to use, which can help guide specific on-farm energy efficiency projects and also renewable energy projects at the micro-generation level. So with that, I'll stop at that, and thank you for your attention.
That's great, John. Thanks very much for that. Again, I appreciate we're under a little bit of pressure today, given that we have two speakers, but a lot of information there. And of course, people can go back and click on those links within the presentation on the website. Barry, if I could get you to come back to us as well, and we'll have a general discussion, and we'll go through some of the questions that are coming through. Just a question I have, Barry. You mentioned Energy Eye Academy. Could you tell us a little bit more about that, or where people could find out more information about that?
Yeah, it's on the SEI website. You have me turned off. I think you have to allow me to start the video there again. Yeah. Yeah, so if you go onto the SEI website or just Google SEAI Energy Academy, it's a recent development, and it's really aimed at a lot of businesses, not so much towards the agricultural industry at the moment, but it would feed a lot of information to people that have, you know, businesses like potato cooling units, or you know, where a lot of energy would be used, especially in the horticultural sector, or poultry units or pig units. It would be relevant to them as well, you know. And it goes, there's various stages that you have to go through to get to the final point of it, and you have to answer questions at the end of it as well. It's a bit like a tutorial, an online tutorial, and you're given some information initially, and you have to answer questions at the end of it. So there's kind of a learning process in it. I think it's quite good. It's a new way of giving information and transferring the knowledge. It's, if you go to seai.ie and onto their website, you'll find the Energy Training Academy.
I have a big question for you, Barry, just in relation to a point that you both made about in terms of the levels of adoption of these technologies, both renewable and energy efficiency. What needs to happen at policy or a funding point or you know, what levels of adoption are we at already? Do we have that information? And how can we support that more in the future?
Yeah, I suppose because there's nothing new about renewables, and there's nothing new about these technologies. They've been around for quite some time, and to move away to a renewable technology, say like solar PV or anaerobic digesters, you know, it all has to make economic sense and give a payback. In a lot of cases, it actually is making a payback without any subvention at all, depending on what your energy use is. If you look at things like accelerated capital allowances or tax incentives that are associated with them as well, so they can give a payback in quite a short period of time. I suppose most people look at it from the point of view, will I get a payback of under 5 years? And if that's the case, I'll go for it. But you know, it depends. Like AD certainly is a technology, or biogas is a technology that will definitely require subvention. It will require in the form of a refit tariff or a RES, a renewable electricity support scheme that's ring fenced for anaerobic digestion or biomethane production, because the cost of that technology is so high. It does require that level of some kind of support. Just like wind and solar PV require support as well, especially on a large scale. You know, and there are supports there to the TAMs for the likes of solar PV, which the Department of Agriculture has granted at a rate of 40%. And it is given a payback, and you know, around the 5-year mark. And you do get the accelerated capital allowances, which many people mightn't be aware of. And I think that's quite a good incentive, especially in a year where there could be a high tax bill. That's going to give you an additional potential payback as well.
Okay,
so
I have to stop you there because we have a lot of questions to get through here. Pas, you have some questions coming through there.
Yeah, there's a question from James Kane, which I think you've touched on in relation to uptake, and he's looking specifically at the pig producers. They're normally very quick to invest, and just looking at why maybe they haven't invested. And I just might put another piece to that, just to John, in relation to our dairy units. What proportion of our dairy units would you now say have I suppose optimally efficient systems? I'm just trying to get an idea of the extent of the job that's out there in front of advisory people and others to try and get that efficiency up.
Sure, yeah. In summary, really, Pat, it's an enormous task. So if you look at, you know, the different technologies that we spoke about, each one has a different sort of level of adoption currently. The plate coolers being by far the most widely adopted. You know, they've been around since God knows when. You know, they've been kind of a standard fit out really on a lot of farms for many, many years. Although having said that, like, the adoption level isn't 100%, it's more like 60 or 70%. So, you know, there's some ways to go on plate cooling, but like that can be probably achieved fairly easily. If you look at other things then, like the heat recovery, for example, that would have very, very low levels of adoption, less than 10%. Solar PV would be in the order of 1% right now. Very, very low levels of adoption on that. And, you know, to be fair, levels of adoption are usually driven by the incentives that are behind them. The incentives for solar PV have only really been filtering through this year under TAMs. So I think it's going to require an enormous task to get 30%. It's achievable. The paybacks there are demonstrated at a certain level of support, you know. So the policy must come first, and then we can drive it on, I think, you know. I think
Barry, on the pig side.
Yeah, I think a lot of on the pigs and poultry have made investments. I was quite surprised though in the last couple of years that we ran an event above in Ballyhaise on energy and poultry, and I was surprised that there's been very little investment in, you know, installation of poultry units across the country, you know, and energy efficient lighting, those type of technologies, and a lot of those can give a very, very quick payback. And there are supports through TAMs to the available for poultry farmers and also for pig units as well to do that. Most, I say 90% of poultry units across the country are using propane gas. And it would make a lot of sense for them to move to biomass boilers through the SSRH, the Support Scheme for Renewable Heat. Since its introduction, there's been a lot of activity, a lot of interest in it from especially poultry farmers and pig farmers. The technology makes sense for them, you know, and they'll be buying in their fuel at, you know, maybe 30%, 40% cheaper than oil would be costing them or propane gas would be costing them. And they're getting the SSRH for 15 years. So I think this is filtering slowly through, and it will, the incentives are there now in many situations. It's just the adoption is what's needed.
Okay. Mark, have you?
Yeah, there's a question there, just it's a straightforward question about this feeding back energy into the grid, Barry. Are farmers getting paid for this at the moment? I know there is a date, I believe is it 2021, where there's an obligation for the state to allow people to feed into the grid. Could you maybe tell us a bit more about that?
Yeah, it's a concept that you see in a lot of countries where, you know, you can produce electricity from the roofs of your cattle sheds, from the roofs of your house, and you can feed it back into the grid, and you get paid a certain rate per kilowatt hour of electricity that you're producing in excess of what you need for your own electricity demand. We don't have that at the moment. If you produce excessive electricity from a solar PV array or a micro hydro scheme or something like that, you will not get paid for that excess electricity at the moment. But there is a requirement that will be on the government, that we will have to have incentives there in place to allow for the payment of renewable electricity. I think it's by June of next year, or June of 2021, so you're correct in that. Mm-hmm. And that will be a game changer there. Because farmers have so much roof space to put PV arrays, and also ground mounted solar as well on a micro basis. You know, what we are seeing on a larger scale is that there was a res auction there, and the results were announced at the beginning of August. That's the Renewable Electricity Support Scheme, and a number of solar PV projects that's larger scale will be going ahead as a result of that. You will see, you know, thousands of acres of land being covered in solar PV arrays, and that's going to be generating renewable electricity. It'll provide an additional source of income for those landowners as well, because they'll be getting a rent or payment per acre or per hectare of land that's dedicated towards solar PV arrays. So those are income generating opportunity for those farmers. It's helping to decarbonize the electricity sector as well, because it's renewable electricity that's being produced. It is possible to potentially graze sheep around those PV panels, and that you can still utilize that land as well. So those opportunities are being generated. But going back to your original question, at smaller scale or micro scale, the sale of electricity back to the grid will be a game changer. I think if we're talking this time next year on this topic, there'll be even more opportunities there.
Barry, a clarification on that, Mark, as well, in relation to the dairy. I think that you know, it's looking like for the micro generation size systems that I mentioned earlier, you know, your 6, 8, 10, 11 kilowatt size systems that are grid connected, it's looking like the export tariff will be fairly low, like at a wholesale rate. So while it definitely will be an added benefit, I think it might still put an emphasis on sizing systems for self-consumption, rather than, we'll say, filling dairy roofs with panels.
You were saying about 80 to 90%. You were saying that it should be targeted towards within the farm gate. Yeah,
exactly. Yeah,
Barry, there's a couple of questions in relation to AD and the type of scale. I think there's a number of large projects that you've mentioned. I think there was an EIP looking at smaller scale. What's your view on the prospect of AD being a real, I suppose, alternative enterprise for a significant number of farmers out there?
Well, there's probably maybe 300, 400 AD units across the country generating, you know, electricity or heat. Now, across Europe, if we look at the model that's been adopted in the likes of Germany, they would have about 9,000 AD units in Germany at the moment. 7,000 of those will be farm scale ADs using many crops. The maize silage will be the crop of choice in Germany. And their farm scale is around 500 kilowatts. And that's the technology they adopted at the time through their renewable electricity supports. Other countries like Denmark, they would have gone for larger scale digesters, or what's called centralized anaerobic digesters, where they'll be much larger, not 500 kilowatts, but maybe 5 megawatts or even bigger. And where a number of farmers, like a cooperative type model, would be feeding into that digester. That digester would be supplying heat to the local municipality, electricity into the local grid. Farmers would take back the digestate, which is a valuable fertilizer, apply it back onto their land. And that model is working well in Denmark, and that's why there are over 20% of the gas in Denmark is coming from renewables at the moment, and that's due to that those centralized anaerobic digesters. In Ireland, I think we're seeing Gas Networks Ireland have a much of an emphasis on biomethane. So that's not using gas or biogas to generate electricity and the byproduct heat, but it's upgrading that raw biogas, which is about 60% methane in it, and would be over 30% carbon dioxide, and then you have water vapor and other trace gases. But the idea is to clean up that gas and remove the carbon dioxide, remove the water vapor and other trace gases, hydrogen sulfide, etc. And that you're left with over 98% methane. That's the equivalent of propane gas. So I think this is the method that we are going to see a lot of emphasis on here in Ireland, is upgrading biogas to biomethane, injecting it into the local gas grids. Maybe some places that are off a gas grid at the moment, that are some towns which are off a natural gas grid, could potentially use this as a model as well, where they could generate their own local gas supply through anaerobic digestion. So I think that'll be the model path that would see it adopted, but that again will require another, I suppose, arm of the SSRH to support it, the support scheme for renewable heat.
And you say those, the scale of those being mixed between the smaller, or does it require us going to the larger units?
Yeah, it does. Yeah, they'll be larger units, probably, you know, the equivalent of a 2 megawatt CHP type AD plant.
Okay, I'm afraid, gentlemen, we're out of time again. Not sure where that hour disappeared to. Thank you, John and Barry, for your presentations, and Pat for helping out with the questions. Just would like to remind you that you can sign up to the Teagasc Connected Digital for free today by visiting teagasc.ie/connected. Thanks to our production team, Andy Boland, Noel Meehan, Pat Murphy and Yvonne Maher. Just also like to remind you, if you do have the opportunity to fill out a short questionnaire that we will send you a link to after this presentation. Next month, we're going to be focusing on biodiversity. So do join us for our next 4 webinars during September, which will be largely focused around policy and the practical measures that farmers can undertake to improve biodiversity on their farms. So for all the team, take care and stay safe, and we'll see you next week. Thank you.